All right, in this unit, we're going to be using the Laplace transform to solve differential equations. And the way that we're going to do this is, say we've got some function of t that we would ordinarily have to apply some very messy calculus to come up with our solution to the differential equation. What the Laplace transform does is it provides us a workaround where instead of doing this, we're going to first transform this into a different domain, from the t domain to the s domain. And we'll talk a little bit more in the future about what is actually going on with that. But we're going to use the Laplace transform to move this into this S domain. And then what's going to happen is instead of some messy calculus, we're going to be applying some algebra here. And that's going to give us a solution. It's not the solution we're looking for. This is going to be a solution in the S domain. But then we're going to use an inverse Laplace transform to get us up to the solution. So this is kind of it's a workaround to get to the solution without dealing with this sometimes extremely messy calculus here. So what we're going to be doing in this lesson is just this piece, just converting, just using this Laplace transform, finding the Laplace transform of a few basic functions, a constant function, an exponential function, and a sinusoidal function, and then also a piecewise function. All right, so let's start with the simplest function that we can think of. Well, actually, let me put up the definition of the Laplace transform. So we've got this capital F of S. And we could also denote this with this cursive L, and then this brace here with this bracket of F, something like that. And then this is defined to equal the integral from 0 to infinity of e to the negative st times f of t dt. So there's our definition for our Laplace transform. So let's start off by finding the Laplace transform of just 1. All right, so that's going to be the integral from 0 to infinity of just e to the negative st dt. Now, I'm not always going to do this, but just for this first problem, I want to note that this is an improper integral. And so what this really means is this is the limit as n approaches infinity of the integral from 0 to n of e to the negative st dt. And we do that because, of course, infinity is not a number. We can't just plug in infinity to find our answer. What we're trying to do is we'll plug in n and then take the limit as n approaches infinity. In the future, I'll just assume that we know what's going on and keep this as an improper integral. But for now, let's plug this in. So we get this integral now is going to be, so this is the limit as n approaches infinity of, well, this is going to be negative 1 over s times e to the negative st, evaluated from 0 to n. So that is the limit as n approaches infinity of If we plug in n here, we get negative 1 over s e to the negative s n minus, if we plug in 0 here, this becomes e to the 0 is just 1, so this is negative 1 over s, so minus negative 1 over s, that's plus 1 over s. All right, and then now evaluating this as n approaches infinity, notice that if s is greater than 0, then this will approach negative infinity, and so e to the negative infinity that's going to approach 0. So I'm going to make a little note here to the side that s has got to be greater than 0, because if s is less than 0, then this doesn't approach anything. This goes off to infinity. So if s is less than 0, this diverges, and that doesn't really help us. We're interested in the domain, on this s domain. We're interested in that, in the values of s, where this is going to converge to some number. That's going to be helpful to us, not the domain where this diverges. So I'm going to make the note that s is going to be greater than 0. In that case, then this is just 1 over s, because this will all go to 0, and we're just left with 1 over s, so long as s goes to, or is greater than 0. All right, there's our first one. Let's now do the Laplace transform for e to the at. So e to the t with some constant multiplied by that t. All right, so that's going to be the integral from 0 to infinity of e to the negative st times e to the at. All right, so then let's rewrite this. That's going to be 0 to infinity of e to the, if we factor out a t, that's a minus s times t dt, which means that this is going to be 1 over a minus s times e to the a minus s t evaluated from 0 to infinity. All right, here, again, if this is infinity, this is going to go to 0 as long as a minus s is less than 0. So we make a little note here that a minus s has got to be less than 0. So s has got to be greater than a. If that's the case, then this is going to go to 0 at infinity. So this is going to be 0 minus. If we plug in 0 for t, we get e to the 0, which is 1. So this is just 1 over a minus s. And so, so our answer is going to be negative 1 over a minus s, or 1 over s minus a. And again, that only works if s is greater than a. So there is our Laplace transform for e to the at. All right, next we're going to do the Laplace transform of sine of bt, where b is some non-zero constant. All right, so this is going to be equal to the integral from 0 to infinity of e to the negative st times sine of bt dt. All right, now this is a little hairier than what we were dealing with before. We've got to use integration by parts here. And so what I want to do is let's get rid of these bounds here, and let's call this y. And so we're just going to solve the integral here, and then we'll evaluate it down the road, because we're going to have to do integration by parts a couple of times on this one. All right, so using integration by parts, we're going to get that u prime is equal to negative e to the negative st, which means that u is going to be equal to negative 1 over s e to the negative st. And v is going to be sine of bt, so v prime is equal to b times the cosine of bt. All right. Now, that means that y is going to be equal to u times v, so negative 1 over s e to the negative st sine of bt minus the integral of negative 1 over s e to the negative st times b cosine, let's put the b up here, b cosine of bt, dt. All right. Now we need to, let's go ahead and factor out this bs. This is going to become positive, sorry, not bs, b over s. And then we'll do integration by parts on this part here. So we're going to get that u prime is equal to e to the negative st. So u again is negative 1 over s e to the negative st, which means that v is cosine of bt and v prime is negative b cosine of bt. And so this now, I've got some room. Y is equal to negative 1 over s e to the negative st times the sine of bt plus b over s times negative 1 over s e to the negative st times the cosine of bt minus the integral of negative 1 over s e to the negative st, might run out of room almost, times negative b. So again, let's make this positive, put this b up here, negative, sorry, this isn't cosine, this is negative sine. Sine of bt, and then our bracket here. All right. So now let me give myself some room here. Let's put this up here. Leave that y there so that we remember that. And then, so now, if we factor out, we get y is equal to negative 1 over s e to the negative st times the sine of bt plus, let's distribute this b over s. So this is going to be minus b over s squared times e to the negative st cosine of bt minus b over s, oh, it times this bs, b over s here, so this b squared over s squared, times the integral of e to the negative st sine of bt dt. Now notice that this, the integral of e to the negative st sine of bt dt, that's y. So we can replace that with y. And let's do that and move this over to the other side, get our y's on the left side of this equation. So we get that y plus b squared over s squared times y is equal to negative 1 over s e to the negative st sine of bt minus b over s squared e to the negative st cosine of bt. All right. So now we've at least got rid of all of our integral signs here, and we're close to some solution. Notice that we don't have any t's on this side, so let's just evaluate this side of this equation now from 0 to infinity. So over here, I'm going to factor out a y here and combine these two. So this is going to be 1 plus b squared over s squared, which is the same as s squared plus b squared over s squared times y is equal to all of this, negative 1 over s e to the negative st sine of bt minus b over s squared e to the negative st cosine of bt evaluated from 0 to infinity. All right. Now, if we plug in infinity here, this both of these terms have an e to the negative st in them. So that's all going to go to 0 as long as s is greater than 0. So let's make our little note here that s has got to be greater than 0. But if that's true, then this all goes to 0 at infinity. And then so this is going to be equal to 0 minus, now at 0, sine of 0 is 0. So all of this will be 0. So 0 minus cosine of 0 is 1, and e to the 0 is also 1. So this is going to be minus b over s squared. And that's, again, s squared plus b squared over s squared times y is equal to that, is equal to now positive b over s squared. So if we multiply both sides by the reciprocal of this, we get that y is equal to, and now this is no longer really y, because y we defined as our indefinite integral here. But now we've applied our integral to this. So this is actually our Laplace transform of sine of bt. This is now going to be equal to b over s squared times s squared over s squared plus b squared. Oh, I'm running out of room. I'm not. So we've got, let me point this down just a little bit, give myself a little bit of room. So this is going to be b over s squared times s squared over s squared plus b squared. And those s squareds are going to cancel, so this is going to be equal to b over s squared plus b squared. And again, s has got to be greater than 0. So there is our Laplace transform for sine of bt. All right, finally we've got the Laplace transform of this piecewise function. And notice that this is not continuous everywhere. There's some jump discontinuity here at t is equal to 5 and t equals 10. And this is one of the things that the Laplace transform is going to help us to deal with. All we have to do for this one, this is going to be equal to our the integral from 0 to 5 of e to the negative st times 2 plus the integral from 5 to 10 of e to the negative st times 0 plus the integral from 10 to infinity of e to the negative st times e to the 4t dt. All right. So notice that this is going to be 0, so we can get rid of that right away. The integral here, this is going to be 2 times, let's see, this is going to be negative 1 over s e to the negative st, evaluated from 0 to 5. And over here, we're going to have, this is e to the 4 minus s t. So this is going to be 1 over 4 minus s e to the 4 minus s t. And we're going to evaluate that from 10 to infinity. All right, here, evaluating this from 0 to 5. If we plug in 5 here, this is going to be negative 2 over s e to the negative 5s minus, well, if we plug in 0 here, this is going to become 1. So this is going to be minus negative. So that's going to be plus 2 over s. All right, over here, if t is going to infinity, again, this is going to diverge if this is bigger than 0. So we need 4 minus s has got to be less than 0, which means that s has got to be greater than 4. So if that's the case, then this goes to 0 at infinity as t approaches infinity, and then so this is going to be minus 1 over 4 minus s e to the 4 minus s times 10. And then s has got to be greater than 4. And there's probably some neater ways that we could write this, but this is essentially going to be our answer. This will be the Laplace transform for that piecewise function.